Very happy to be able to present to you some highlights from BESA research tonight. Thank you for turning up. And we will start the first session by talking about some aspects of source analysis. First discrete source analysis and then also distributed source analysis. And then after the coffee break, we will continue with source montages, artifact correction, time frequency analysis, and statistics. So you will get an overview over the whole functionality that's available. And it's a bit of a challenge to condense this material into the 3 hours, but I will do the best I can. And yeah, and if there's any questions, you can also please interrupt, and we'll sort of discuss that then. So let's start with discrete source modeling. So first of all, we can here see a slice through a brain, and this is just to illustrate that the reason why we are able to measure brain activity outside of the head is that the pyramidal cells, they are aligned perpendicular to the cortical surface. So many neurons then fire at the same time, and because they're organized in parallel columns, their activity sums up, and we can get a measurable current flow outside the skull. And this current flow we can model by a dipole. A dipole has a location, an orientation, and a magnitude. This magnitude, or the strength of this dipole, is proportional to the number of activated neurons, and so it correlates with the area of activation and with a mean dipole current density. And in the first approximation, we can think of the skull as a sphere. And with regards to the surface of this sphere, we can get different orientations of this dipole. For example, a dipole that's active at the cortical convexity has typically a radial orientation, and a dipole in a cortical fissure, like the orange one here, has a tangential orientation. Then there's also other orientations possible, like the red dipole here, which has an oblique orientation. So if we look at the dipole that is at the surface of the cortical sheet with a radial orientation, this will be, this cortical sheet is modeled by an equivalent dipole near the center of that sheet, and this cortical patch can have roughly maybe 3 centimeters in diameter and can still be accurately modeled by one dipole. The problem, of course, that we face in EEG especially is that only a small fraction of the current that's generated actually flows outside of the brain, and most of it returns inside the brain space. So the result of that poor conductivity of the skull is that we get a very large spread negativity, like shown on the left here, that spreads over the over the skin. Due to physics, however, we know that the overall voltage that we measure over the scalp should be 0. So this negativity on the one side is also matched by a positivity on the other side of the spherical conductor, and we need some electrodes in inferior positions to be able to properly pick up that positivity. The second example is activity in a fissure, and here we get a different topography on our scalp. So this map that we see on the left-hand side now shows 2 clear maxima, one negativity at the posterior aspect and one positivity at the frontal part. And in fact, the location of that activity in the brain is underneath none of these 2 maxima, but instead is underneath the region where the dipole where the current density change is largest. So we have the highest density of these equipotential lines on the scalp. So let's look at an example of the propagation of this activity. If we imagine a current in a cortical sheet where we only have one single source that's active, and it has a bipolar activation pattern. So first we have a positive current and then a backflow later on. If we have no propagation of activity, so only this one source is active, then we can see this distributed activity in the center here of the slide over the whole scalp. And if we do a sequence of maps of this topography, we can see that the topography stays stable over time. It shows these two maxima over the whole time and just reverses its polarity at some point. Now if we get to a more complex scenario where we have two currents, two cortical sheets that become active within a few milliseconds of each other, and in this case are approximately 3 centimeters apart from each other, then we can see again at the scalp an overlap of these two topographies that does not show two maxima but only really one clear maximum. And if I look at the topographies now over time, I can see how the map topography changes over time. So if I look at this negative peak here at the posterior part, then I can see how it seems to rotate over time to a more first central and then frontal location. And so if we in our own experiments see maps like this that change over time, then we can infer that there will be more than one source active underneath. We can now face the scenario of trying to account for these activities and to model these activities. So there's two things that we need to do here. First, we need to solve the forward problem. So for a given brain location and source orientation, what do I measure at the site of the electrodes? We can choose, for example, a spherical shell model. Then the question is, how many shells do I need to apply? Or we can use a so-called realistic head model where we use the individual brain and divide it up in compartments of different conductivities and then model the current as it flows through these compartments. So BESA research uses a 4-shell ellipsoidal model by default. And we also have realistic approximations in BESA research. These are finite element models of average brains with different, for example, for different age groups, especially for children, very interesting. And then we also have the possibility to generate individual finite element models in combination with BESA MRI, which we'll see later. Right, and we also have the inverse problem. The inverse problem is what we really need to solve. So which brain sources explain the signal that I measured outside the skull? And for example, this activity here in the center with a large central negativity can be explained by one single source in the center of the brain, like the one here on the left. It can be explained by two sources in the two auditory cortices, or it could also be explained by large patches of activation over the cortical sheet on both hemispheres, or many other scenarios. So there is a multitude of potential constellations that can equally well explain my data, and that means that I need to put some additional knowledge about my experiment and about the expected activation into this problem to solve it. We talked about the forward problem, and the solution of the forward problem generates the so-called lead field. So the lead field is a matrix that for each source in the brain tells us what we will measure outside of the skull at our electrode sites for this particular source. And if there are several sources, then the lead field simply gets several entries. And the physics tells us that the so-called linear superposition principle holds here. That means if I have several sources in the brain that are active, then they will simply add up to generate the data which I measure. So here in this slide, the data are shown on the left. Then I've got, in this example here, 3 different sources. And the 3 different sources will give me 3 lead field entries, which are then multiplied by the activities of the source to generate this data on the left. And there's then some residues, so some data that I have not explained with my lead field times the source activities, and this can be partly measurement noise, partly brain activity in the background that I have not modeled. Yeah, and also errors in my head model can contribute to this residue. So I can now take this around and instead of saying lead field times source waveforms equals my data, I can invert this lead field matrix and apply this linear inverse to the data. And if I do this, then I get my source waveforms. So simply by inverting this matrix, I can apply it to the data and get to an estimate of my activation of the sources. And this is basically what we use in the dipole fitting. For dipole fitting, I need to follow a few principles. So first of all active cortical regions need to be explained by one dipole each. This dipole in our spatio-temporal model, which was proposed by Michael Shirk and others, this dipole will not move over time, but its activation pattern can change. So a dipole can also be silent. It can have no activation at some point in time and then become active later. The challenges here are how many cortical sources are active, and do I potentially have bilateral activities? That means that one variation in the data needs to be accounted by 2 dipoles in the 2 hemispheres, and potentially I may have overlapping activity where different dipoles become active simultaneously or shortly after one another. So an example that we can study now is a median nerve stimulation. On the left here, you can see the scalp distribution of that measurement for the left median nerve stimulation. On the right, you can see the the maps that were generated at different times after the stimulus. And again, we can see that the map topography changes over time, and so we need to try and model this with a source reconstruction. For example, if we have 2 local currents in 2 different cortical patches, we can try and reconstruct them by 2 sources, and in this case we will be able to model the data in an accurate way, and then our multiple source model will reconstruct these source waveforms accurately with the addition of some noise. However, if we try and account for this activity in 2 cortical patches with a single dipole, simply, for example, by fitting a dipole to the maximum of the overall activity that we measure on the scalp, then we will get to an error, and the single dipole will localize most likely somewhere between the 2 patches that are the correct solution, and also the source waveform will be a compromise of the 2 source waveforms that were originally in the data. So the typical fit procedure looks like this. We first assume that a single dipole will explain the early onset phase. So the initial hypothesis is a single equivalent dipole. Note that this assumption is not a good idea for bilateral activation like an auditory stimulus. Then we will need to start with 2 simultaneously active dipoles. So if I use the head model that I've chosen, I can then estimate a topography, and this can be inverted to give us a source waveform by applying this inverse to the data. The source waveform, now again with the forward model, will give me model waveforms. So now I can make a prediction on if this was my correct source position, what would I have measured on my scalp? And then I can look at the difference between the 2, the source, the model waveforms and the measured scalp waveforms, and I can relocate the dipole and go through this whole process again until I get the best match between my model waveforms and the scalp waveforms in this fitting interval. So I would start with some small time period where the activity starts, and then I have my first dipole located. Then I will find out that there's a residual, so the red data here are now the residual, and I can see that there's some large unexplained data later on in the time course of the activation, and I can start with a second source. So I will leave this first source as it was, and now add a second source, and now I have a forward model that contains two topographies, which again are inverted to apply to the data to give me the source waveforms. I can then make a forecast on the measured data if these were the correct sources, and minimize this difference by changing the location of the second dipole until I get the best match between my model and measured waveforms. And once I have the best match, I can see here the red lines now are practically zero, and I've got a very good fit that explains my data well. Yeah, what about if I add more sources to my model? So can I have too many sources? So if I think of two sources that I had already, and now I add a third source at a different position, with now I have three waveforms. So what would happen now in my reconstruction of the source waveforms if, say, only the red source was active in the brain? Well, the inverse operator will achieve the result that the activity of the red source gets reconstructed well, and the other two sources will not show any activation because I've already modeled my activity correctly using the red source. If the blue source becomes active, then again the reconstruction will lead to a good reconstruction of the blue source activation, and I will have a silent red and green source. And if the red and the blue are active, then both of these will be reconstructed, but again the green source will stay silent. So as long as I have modeled my activation in all active brain areas, then I can always add more probe sources and they will not pick up any activation. So this was a brief introduction, and now we're going to try this out on the BESA research software. So let me move to the program BESA Research. I hope you can see it okay. And I'll now open a simulation. So we're going to start with some simulated data in order to understand the principles on real data, and then work with a real experiment later on. So the first one I want to use is a simulated experiment where I had a biphasic activation of the two auditory cortices, and you can see there's no noise in this data. It's a very clean data set, and we now want to try and fit this data in the BESA source analysis module. So the first thing I do is that I can drag with my left mouse button over this data and then right click to get a context menu. And in the context menu, there's an entry called Source Analysis. And then I get the chance to make some adjustments to the data before I send it to the Source Analysis module. So in this case, I'm just going to work with the whole data segment and not apply any filters to this. And then the Source Analysis module opens. And this is the view that you get. So on the left-hand side, you can see the measured data, and on the top of that, you can see a butterfly plot of all channels. Then in the center, at the top, you can see the global field power, and this is displayed in a logarithmic fashion. So the 100% here is like the normalized of the highest field power, and then you get 10%, 1%, etc. And the bottom section of the central part here is the area where the source waveforms will be shown once I have created a model. So let me just check that I've got the correct source type. Then I'm going to double-click into these head schemes to create two sources. So and now I have created a solution with two dipole sources just by clicking into the head schemes. Of course, they don't show the right positions or orientations now. They just show me two sources, and I immediately get a reconstruction of some source waveforms in my central window. And now I want to fit these sources, so I'm going to work from with a fit interval from the onset of activity to the peak of activity. And I will fit both these sources, so I click on this button, All Fit, and then Start Fit to perform the dipole fit of these two sources. And what I can see now is that after fitting these sources, I get a line here for the residual variance. So this is the unexplained variance in the data, and that is actually almost zero. So I've got a perfect model for my data with a perfect explanation. I can scale up these activities a little bit. And I can also invert the orientation, because these are auditory sources, so they should point down into the ordanum temporale. So I'm going to press the I key on the keyboard for inverting their orientation, and that will simultaneously also invert the source waveform. Because mathematically it's the same whether the source points upwards and has a negative current, or whether it points downwards and has a positive current. This is for the mathematical solver of the equation, it's the same thing. But of course, physiologically, it can make a big difference. So what would have happened if we had modeled this data set with a single dipole incorrectly? To check this out, I'm going to switch off these two sources briefly, and I'm going to add a third source. Now this is the only active source, and I'm going to fit this source over the same fit interval. And we can see that this fit interval, this source fits into a location that's a very good compromise between the two correct locations of the source, and the residual variance is still less than 1%. So I get an almost perfect explanation of my data, because 1% is a very good value in case of noisy experimental data. So how can I now know whether this is the correct solution or whether the other solution is the correct solution? Well, from the talk previously, we should now expect that if I switch these other two sources on, then they should pick up all the activity, and the third source should be silent because it's in a probe location that's not the correct location. And this is not quite true. You can see now that there's still some activation of the third source. And the reason for that is that there's a thing called regularization that is applied to the inverse operator. So we smooth this inverse operator a little bit, and this results in some leakage of activity from the two sources to the third source. You can see at the top here there's a writing RC1, and if I click on that, you can see that this is a regularization constant, difficult word, and I can change this from 1% to 0%. And now I can see that indeed the activation is completely separated, and I can get a perfect construction of my activity with the two dipoles and zero activity in the third dipole. Okay, so why don't we always work with 0% regularization? The reason is visible if I change my example to a more realistic example with some noise in it. So I'm now going to go back to the main program and change my file to the same simulation, only that some noise was added here. So let's now use this data set and do source analysis on this one. If I again drag and right click over this, I can now see at the bottom that my last chosen epoch and filter settings have been recorded and are available here. I can click on that, and now I can upload the same segment only with the noisy data to the source analysis module. Yes, and I can see that with this regularization constant of 0, now I get a much more ugly representation of these waveforms. So there's still a reconstruction of the waveforms, but there's a lot of noise that gets added. And if I now change this regularization again and I make it larger, then I can see how my noise reduces considerably, and at the same time my green source picks up some activation. So we've always got this trade-off between a perfect separation of activities of sources and noise that we add by this strong separation. So if I go up to the maximum of 20%, then I can see that all three sources have roughly the same activity. And if I go back to maybe 2%, then I get sort of a better signal to noise, and still some activity is left in the green source. This, I have to say, this is a very strong example because these three sources have got very similar topographies, so it's very hard for the inverse operator to contrast them against one another. If I switch this source off, then I get immediately a better reconstruction of the source waveforms with less noise in it. So in a real example, you will not get such an extreme case where you have to contrast sources as much as this. So this was the simulation. Now what about the real data? So I'm going to close this module and not save the solution. And I want to show you some real data. So let's open another data set that I should still have here, which shows a grand average of an auditory intensity experiment. So this experiment was done on 10 subjects, and each subject was subjected to auditory tones of different levels of intensity, from 60 decibels up to 100 decibels. And we can here see the different averages of these conditions, including one with the low intensity, which is a sum of 60 and 70 decibels, and then there's a high condition that contains a sum of the 90 decibels and the 100 decibels. And we want to know, can we reconstruct this activation, and is there some difference between the low intensities and the high intensities in the way that the brain responds? So let's start with this low condition. I'm going to drag over this and right-click to start source analysis. And again, I've now got the chance to refine this selection, and I'm going to work with a smaller subsegment. So I will choose -50 to 250 milliseconds. And the filters will be adjusted so that I have a low cutoff filter of 0.5 Hertz, which will smoothen the baseline a little bit, and a 40 Hertz high cutoff filter. Yeah, let's do this. So we enter the source analysis window, and we can see the the waveforms on the left-hand side. And the global field power is here in the top. We can see a small peak here at the 44, 48 milliseconds. This is the P50. But it has less than 10% of the global field power, so we will not be able to fit this. We will concentrate on the N100 at around 100 milliseconds with the largest global field power. So let's double-click twice into the head schemes to generate two dipoles. I know that I need two dipoles because it's auditory activation. I will also use a interval with the onset of 76 to 100 milliseconds. To check what is a good interval, I can use the principal component analysis. So this button PCA here, that shows me that 99.4% of the activity in this time interval is explained by a single PCA component. So I can be very sure that if I fit this time interval, then there will be no additional extra activity that will change my dipole location. So I press All Fit, Start Fit, and the two sources do fit roughly into the auditory area, but we can notice that the blue dipole is quite a bit more frontally oriented than the frontally located than the red dipole. So also one of the sources may be slightly too medial, the right one. So we can improve the fit by adding a symmetry constraint. So we can make use of our anatomical knowledge. We know that these should be in symmetrical areas in the auditory cortex. So this location parameter here that says free here at the top can be changed to make the source 2 symmetric to the dipole source 1. And now I can repeat this fit and see what the result is. So All Fit, Start Fit. And I can see that now I get a symmetrically aligned fit, and both of these sources are now in the auditory areas where I would expect them. I just need to invert the orientation of this blue dipole to make them equivalent. And what about the residual variance? So with this symmetry constraint, my residual variance in the fit interval is 1.1%, as I can see here at the top. And if I go back with Control Z to my previous fit result, then I can see that before it was 1.03%. So I had a better residual variance, but I also had a worse explanation of my data in terms of physiologically correct results. So the residual variance is not always the only criteria that we should look out for to explain our data. Now let's have a look at the general residual variance after this fit. So if I press this res button at the top left, I can see the red lines for the residual variance. And if I just look at the residual variance without the data, so I can see that, scale it up a bit, in this fit interval between 76 milliseconds and 100 milliseconds, I've got a very good explanation of my data. But later on at the N150 and also at the P50, I don't have such a good explanation. And here we can now introduce the concept of regional sources to make this better. So we're now going to make a new solution. And a new solution is created just by typing the N for new key on the keyboard. And I want to change this into regional sources. So I'm going to use an option parameter here to change the default source type from a dipole to a regional source. So now it's a regional source. And what is a regional source? It is a source that has one location but three orientations. So basically it can model all activation that comes from a certain brain region, no matter what orientation it has, because it already has all three orthogonal orientations. And so it's a very robust estimator of any activation in that cortical region. And it's in BESA it is displayed as a diamond shape. So I can see here I've got one regional source now, and I can add a second one by double-clicking. And now I've got an initial model with two of these regional sources. And because they have three orientations, we can also see three source waveforms here in the central display. So now I can just try and fit this over the whole time area, because I know that the whole activation here happens in the auditory cortex. So I'm just going to use the fit interval from 40 to 172 milliseconds, just from the P50 right through the N150. And now press All Fit, Start Fit. And I can see that even though I have not imposed any symmetry constraint yet, I already get a much more stable fit for these two sources. And the residual variance is pretty much smaller than it was with the dipoles in this fit interval. Of course, I can also use my symmetry constraint to maybe get even better, make this source symmetric, repeat the fit, and then I get a slight improvement maybe in the localization again. Yeah, and now we can play with these three orientations of the sources to make them explain the different components of this auditory experiment. So I can start with source number 1. So I'm gonna select the source, and now I can right-click here somewhere in this area, and from the context menu there's a entry called Set Orientation, and that gives me the submenu entry Set Orientation 1 at maximum. Yeah, and this is what I'm going to do. So now the three orthogonal orientations are rotated around so that the first orientation explains all the activity at the maximum, and the maximum is the N100. So I'll do the same for the second source, and now I've got them rotated so that they explain the N100, and automatically the other two orientations are also adjusted so that the second orientation tries to explain most of the rest of the activity. And I can refine this again if I want to, if I click on the N150 and right click here, and now I can set orientation 2 at the cursor position, and similarly for the other source, set orientation 2 at cursor. And so this is now my finished result for explaining the N100, the N150, and I also get some explanation of the P50, although that's very small, but I've got a very good explanation of these two different activations. So with my regional source model, I have actually gained some more robustness and also explained the data completely. If I look at the high condition, that was the condition where we had the additional, where we had a stronger intensity. So I can also send this to source analysis. So I'm going to drag over the high, right click here, use the same settings as I did before, and send us to source analysis. And I can now see, if I look at the residual, that there's still some large unexplained component for data with high intensities. So looking at the PCA, I can see there's one PCA component that dominates this high condition. So if I switch back to the low condition with these arrows, I can see there's hardly anything unexplained, but with the high condition, there's this large PCA component that is unaccounted for. So I'm now going to add an additional source, double click, and I'm going to fit over this interval and try and explain this activity with the third source. So I'm going to stay with these two sources that explain my initial auditory activation. They're going to stay there, and I'm just going to fit the third source, start the fit, and I can see that it moves into the area of the anterior cingulate cortex. And if I can orient it, let me just do this, set orientation maximum, then I can see there's one large activation of one orientation. The other orientations do not play such a big role here. And I can have a look at the anatomy. So I press the A key on the keyboard for anatomy, and this shows the average brain. I can switch to the view with 3 slices and one 3D head, and I can see that indeed this green source ends up in the area of the anterior cingulate, and the other sources, if I highlight them, they end up close, but not exactly where the auditory cortex is, but very close to the position of the auditory cortex. So this completes my model for the high condition. And if I go back again, switch back to the low condition, you can see this green source is not active in the low intensity condition, but I can switch back to the high and I can see how it emerges when we get the higher intensities. So yeah, this concludes the model. We can now save this as a solution. So we can, from the file menu, save the solution as all subjects CC. Yeah, I'll call it test because it's my test solution. And yeah, this now concludes a discrete source modeling. And I just want to mention a few conclusions or takeaways. So we need to fit or place sources into all brain regions that contribute to the data. And we need to be aware that one source actually models an area of roughly 3 centimeters in diameter. So we cannot get to a better resolution. So if two areas are very close together, it's going to be very hard to separate them from each other unless they have different orientations. Then it gets easier. Yeah, regional sources are more stable in conditions with noisy data, and they can help you to get to better fits. And very often the brain responds to a stimulus with bilateral symmetrical activation. So this should be kept in mind. You sometimes need bilateral sources to account for one PCA component. And in terms of how many sources do I need, it's always useful to look at the PCA of the data and see how many components there are, that then I'll know I will need at least as many sources as the number of PCA components. When I start with a new model, I will look at the PCA usually, and I will look for the first activity, so where the global field power rises, and then find an interval where I've got nearly, this should be more than 95% of activity should be accounted by one component. In MEG, maybe a bit less than 95. And when I can change my interval and see if it changes. So if I make it too large, you can see now the PCA component here reduces to only 94%. So if I go back and just use the onset to the peak, then I get to nearly 99%. But the PCA is the first indicator. And then once you've got the model, then you start looking at the residual, and then you check for leftover activity that has not been modeled in the first modeling step, and then you can account for this by trying again to mark a fit interval that only that gets as much activation into this remaining PCA component as possible.
Okay, so it's not an automatic process, but we make trial and error sometimes, right?
Yeah, dipole fitting is a little bit of trial and error. So, and it's easier if you start with the condition where you have less complex activation. So in this case, if I go for the low condition first, and go and try and model this one, then I've already got so some reduction of my data. Let me just go to the data. So so now I've got a good fit for my low condition, because in the low condition I've got less complex activation. Now if I go to the high intensity, I can build on this low condition and ask which additional activation did I get. Or another example we have is where we have a visual motion experiment, and we had two conditions. One was a static pattern and one was a moving pattern. So we then used the static pattern to find the sources in the first visual processing area, in the V1. And then we added, we kept these sources and then analyzed the motion condition, and then we could add more sources to it. But if you start with the motion condition, you've already got a more complex activation, and it's more difficult to fit these cycles. So it's always better to start with sort of easy and work to the more complex. And similarly, to start with the early activation and then work to later components, one after the other.